So yes, as a reminder, anybody that didn't take the homework quiz yesterday is taking it today, so I will pass those back tomorrow. And then tomorrow is a review class period on 4.1 through 4.4, first half of chapter 4, summative quiz on Friday. So there's not another homework quiz before Friday's quiz. Today, we are building off of what we did yesterday. Yesterday, we looked specifically at operations with pure imaginary numbers. So those were just terms that had I. Just as a review, what does I represent? Square root of -1, yes. So I, you always leave it written as I, but knowing what number it represents is important, so you're not changing it to something else later. Today I guess we're building on this. We are now doing operations with complex numbers, so we not only have imaginary parts to a complex number, there's a real part. And I did preview this yesterday. Any complex number can be written in the form a plus b times I. So yesterday we just focused on the b times I part of it, and now we also have the a. So a lot of times you will see parentheses written around these, and that's just because a plus b times I represents one number. So it looks like two separate numbers together, but it's one number. A and b do represent real numbers in that expression. I is the imaginary unit we talked about yesterday. A is called the real part of the number because it does not have the imaginary unit attached to it. And then B is called the imaginary part because it is attached to the imaginary unit I. So it does give two examples of just complex numbers written out. So if we have 5 plus 2I, the 5 would be the real part, and then the 2I would be the imaginary part. And identifying real and imaginary parts of a complex number, it's important when we go through example 1. So it gives another example. If you have 1 minus 3I, your b value is really -3. But then I did include this Venn diagram here because this shows how complex numbers are broken down. So like I said, every number you work with is a complex number, including real numbers. So all complex numbers are of the form a plus b times I, and then what it explains over here is also included in this Venn diagram. If your b value is 0, so this would be a plus 0 times I. 0 times I is just 0, so this would just be a. A is a real number. So if the b value is 0, you have a real number. So that's why complex numbers are either real or they're imaginary. If the imaginary part is 0, you have a real number. If b is not equal to 0, that means you have an imaginary part, and therefore you have an imaginary number, with or without a real part to it. So if your a value then is 0, that would mean you do not have a real part. That would just be b times I, and that's a pure imaginary number. Those are the numbers we worked with yesterday. So that just breaks down our complex number system that we work with. But then what we're going to be using to answer example 1 is knowing whether or not two complex numbers are equivalent. So two complex numbers are equal if and only if their real parts are equal and their imaginary parts are equal. So it gives two complex numbers, a plus b times I and then c plus d times I, and these are only equal to each other if a and c are equal, so their real parts are equal to each other, and then b is equal to d, so the imaginary parts are equal. So we're going to use that fact in example 1. So if you see a problem that asks you to find values of x and y that make this equation or this statement true. So notice We have 5x plus 1, and then we have 3 plus 2y that's being multiplied by I. And then on the other side of the equal sign, we have 2x minus 2, and then y minus 6 that's being multiplied by I. So we could say that each side of this equal sign represents a complex number or a complex expression. And you first want to identify what's the real part of each side and what's the imaginary part. The real part is going to be anything that is not being multiplied by the imaginary unit I. So on the left side, the 5x plus 1 is not being multiplied by I. That is the real part. And on the right side of the equal sign, the 2x minus 2 is not being multiplied by I. So that is the real part on that side. And then identifying imaginary parts. So on the left side of the equal sign, the 3 plus 2y is being multiplied by I. That's the imaginary part. I'm just going to abbreviate imaginary there. And then same with the y minus 6 on the right side. So for that equation to be true, for those two expressions to be equal, the real parts have to be equal and the imaginary parts have to be equal. So you're going to set up two equations to then solve for x and y. So I'm first going to work with the real parts for these two parts to be equal. That means 5x plus 1 must equal 2x minus 2. And I can then solve that equation for x. So solving for x, I can subtract 2x from each side. And that would be 3x plus 1 equals negative 2. Subtract 1 from each side. So 3x would equal negative 3. And then divide by 3. So x is negative 1. That's the value that makes the real parts equal to each other. And then you would follow a similar process to find the y value. So again, for this statement to be true, the imaginary parts have to equal each other. So I know 3 plus 2y. I don't have to include the I, but 3 plus 2y must equal y minus 6 in order for the imaginary parts to be equal. And if I solve that for y, here I can subtract y or 1y from each side. So I have 3 plus y equals negative 6. Subtract 3. So y would equal negative 9. That is the y value that makes the imaginary parts equal. So if x is negative 1 and y is negative 9, then our equation is true. So again, what you would need to be able to do is identify what's real, what's imaginary, and then know how to set up equations to make two complex numbers equal to each other. Any questions on that example? That's it. Yep. So the new part, I guess, would be identifying what to set up in your equations. Nope, you certainly could. So that would be a way to check, is then substitute these in to see if you have the same thing. But the question just said find the values of x and y. So the values of x and y, those are your answers. You don't have to put it in an order pair. No, it's not a point. It's just two separate values. All right. Then some of the examples today, I realize we're working with complex numbers. The imaginary part of a complex number is newer to us. But simplifying expressions in algebra is nothing new to you. Simplifying expressions is not new. So some of this, rather than me leading you through it, I want you to use what you already know to answer the question. So example 2, there's 2 examples. I'm not going to lead you through these. I want you to try them on your own first. So you are just simplifying each expression. In A, you are adding. In B, you are subtracting. So I want you to think about what you already know about simplifying expressions in math to simplify those two expressions. I want to give you a chance to think through it before I discuss it with you. And then we will discuss together, make sure you all have the right answer. I'll walk around, see where you're at. You can ask me questions. I just want you to try it without me telling you what to do first. You are adding for part A. FOIL would be multiplying. Double check what you have. A should be -1 minus 2i or -1 plus -2i. You wrote it that way. B is 5 plus 4i. So a few things I want to say. So I need your attention, please. What can throw some students off with these are the parentheses. So the only reason for A, since you're adding, the only reason you have parentheses around both is because it's saying you have one complex number added to another. But A would be as if there's no parentheses. You're just combining like terms. Careful, though, when you are subtracting, that you are either distributing that negative through, like I rewrote it here, and some of you did that as well, or at the very least, make sure that you are still subtracting that 2i. Some of you wanted to add it, so make sure when you're subtracting that you are subtracting all the way through that second quantity. But adding and subtracting complex numbers is just adding and subtracting like terms. And your answer would still be a complex number. So are there any final questions before we move along? Okay. Then for example 3, this one involves multiplying, but as part of an application. So in an AC circuit, the voltage V, current C, and impedance I are related by the formula V equals C times I. And then it says find the voltage, so we're looking for V, in a circuit with a current 2 minus 4j amps and impedance 3 minus 2j ohms. So I'm going to start out, I'm just going to copy down the formula that you're given. Voltage equals current times impedance, C times I. And we're finding voltage. And we are given the current, so 2 minus 4j is your C, and then the impedance, 3 minus 2j is your I. So I'm going to substitute those quantities into the formula, and make sure when you do that, that you're putting parentheses around them because they are being multiplied. So V will equal 2 minus 4j multiplied by 3 minus 2j. Okay, so that's the setup for this. Now, I realize they're using J and they're not using I, but these are complex numbers. In this application, J represents I, meaning J in this case is representing the square root of -1. So what I would like you to do, I'm going to stop here. I'd like you to finish this. I'd like you to continue simplifying to find V. So use what you already know about simplifying expressions like this to simplify it. And also keep in mind, J is representing I. So I'm just going to say that, and then I'll walk around. I can check what you have. We'll make sure we're all understanding it. But again, use what you already know about multiplying those kinds of expressions to simplify. Is right so far. So now remember J represents I. So yeah, yes. let's take your answer. So J squared. All right. I know some of you are still finishing up, but double check. The box works okay. The box is foil. It's just a different organizational piece. All right. So for these, you do FOIL. When you multiply complex numbers, you FOIL. With your last term then, when you multiply j times j, in this case, j squared represents I squared, and that's -1. Remembering that from yesterday? So you'd replace the j squared with -1, meaning it's 8 times -1, so that'd be a -8. And then you can combine the 6 minus 8. So overall, -2 minus 16j, or if you had -16j minus 2, that's the same thing. And then if you didn't have this, I wouldn't take off, but voltage is measured in volts. So it'd be -2 minus 16j volts for the voltage. Questions there? We're going to be using FOIL more in the next set of examples. All right, so then for the next piece, few things that you need to understand and not just know a process, but understand why you're doing it. So before we look at example 4, we have two complex numbers if they are of the form a plus bi and a minus bi. So they're not the exact opposite of each other, but one is a sum and one is a difference. One's plus, one's minus. These are called complex conjugates. So the real parts are the same, the imaginary parts are the same, but the sign is different. The product of complex conjugates is always a real number. So if we multiplied these two negative numbers, a plus bi and a minus bi, we would get a real number as our product. So we're using this fact when we simplify the quotient of two complex numbers. The reason these three examples under example 4 are not simplified is because to be simplified, you cannot have an I in the denominator. And all three of these have I in the denominator. So to simplify these, to get I out of the denominator, we actually do this same process when we get to radicals. That'll be in a later chapter, but the process will be the same. We multiply, and we're multiplying both the top and the bottom of the fraction, but we multiply by the conjugate of the denominator. And that's important that you're multiplying by the conjugate of the denominator, not the conjugate of the numerator. So if we look at example A, I have an I in the denominator, so it's not simplified. And my final answer is still going to be a complex number in the form a plus b times I. So to simplify this, I first want to multiply both the top and the bottom by the conjugate of my denominator 1 minus I. The conjugate is going to be 1 plus I. So I just changed my subtraction sign to a plus sign. If it was plus, I would change it to minus. And I multiply by that same thing on the top. The reason you have to multiply by the same on top and bottom is you're really multiplying by a fancy looking 1, so you're not changing the value, you're just changing the way it looks. It's kind of like if I just multiplied by 2 over 2, it's just 1. So when I multiply across, and now you're using FOIL to multiply across for both the top and the bottom. All right, so on the top, if you FOIL, you'd have 2 times 1, that's 2, plus 2 times I is 2I. And then for the inside, I times 1 would be plus 1I or just I. And the last term's I times I is plus I squared. So make sure when you're multiplying I by itself, or anytime you multiply a variable by itself, it's squared, or you add the exponents. And then on the bottom, if you FOIL, you have 1 times 1 is 1. 1 times I would be plus I, or 1I. And then the inside terms, negative I times 1 would be minus I. And negative I times I is minus I squared. Okay, so I'm going to look at the bottom first. What happens when you multiply conjugates? Your middle terms will always cancel out. Positive I, minus I, those cancel each other out. And then I have an I squared on the top and the bottom. I squared we just talked about is negative 1. So here when I have plus I squared, that's really minus 1 here, or plus a negative 1. On the bottom, when I have minus I squared, that's really minus negative 1, which is really plus 1. So here's what I have. On the top, I can then combine the 2 minus 1 that I have, and that's 1, plus my 2 middle terms, 2I plus I is 3I. On the bottom, I have 1 plus 1, and that's 2. So the bottom is now a real number. The i's are gone. That's what happens when you multiply by a conjugate, and you cannot have I in the denominator. Okay, so now I still need to write this in the form a plus bi. Right now it's a fraction. So I'm going to split this into 2 fractions. I have 1/2, that's my real part, plus 3 over 2i is my imaginary part. So I'm just splitting the numerator into those 2 fractions. Both have a denominator of 2. 1/2 plus 3/2 I would be the answer. And for those fractions, if you wrote them as decimals, they'd be okay because they're terminating decimals. Questions on part A? Okay, and make sure you understand that goal of getting the I out of the denominator. That's the whole reason you're multiplying by the conjugate. So if we look at B, this one is set up a little differently, but we still have an I in the denominator. And you still follow the same process of multiplying by the conjugate of the denominator. So if the denominator is positive 2i, what do you think the conjugate would be? Negative 2i. This is like a 0 plus 2i, so the conjugate would be 0 minus 2i, which would just be negative 2i. And I can multiply by that on the top and bottom. What's different here, though, is you don't have to FOIL. So on the top, you just distribute the negative 2i to the 5 plus I. And on the bottom, you just multiply the 2 terms together. So on top, we would have, if we distribute, negative 10i, and then minus 2i squared. And on the bottom, 2i times negative 2i is negative 4i squared. And then I can simplify from there. So I have negative 10i. Remembering that I squared is negative 1. So if I have a minus 2i squared, that's a minus 2 times negative 1. That's really then plus 2. So it's kind of like just changing the sign of the number you have in front of the I squared. So a negative 4i squared is negative 4 times negative 1. That's a positive 4. So now again, your i's are gone in the denominator. So to split this, I'm actually, if you didn't do this, I wouldn't mark it wrong. But I'm going to write the real part in front. So I'm going to write the 2 over 4 first. So I have 2 over 4. And then because of the negative 10, I can just write that as minus 10 over 4i. But here you want to make sure if you're leaving it as a fraction that they're simplifying. So this would really be 1/2 minus 5 halves I. And that would be the final simplified form. Right, you want to make sure it's still written as a complex, like in the form of a complex number. If you left it, you'd still have to simplify, like 10, 4, and 2 can all be divided by 2. So you'd still want to make sure this is 5, 1, and 2. But you'll see, like if you're working on the practice, all of the answers are going to be written in the split form. Okay, so I realize we have a few minutes left. I want to point out one thing. There is practice in the book for this. Odd answer in the back. I'll have evens on the board tomorrow. But with the few minutes remaining, try example C. And I'll give you a few minutes. I'll put the answer up here so you can check. But try it. Make sure you understand how to simplify these on your own without me leading you through it.
So we distribute the 5. Yes, and then happy you just distribute it. And then you only switch the middle sign, right? You don't have to move like it like negative or anything. Right. Okay.
Yeah, we only switch the middle one. Yes. Yep, so that's right so far.
When I get to this point, do these eyes cancel out?
No, they don't.
So,
This should have canceled here, though.
oh yeah. Okay.
So you want to multiply by the conjugate, meaning this stays positive 3. You only change the middle sign. So you're not making it the opposite, you just change the middle. All right, I do have up here, if you want to check if you either have it or check what you have so far. Or if you want to write down what the answer is, if you want to still look back at it. But note there's still practice there. So even if you feel awesome about what we did in class today, doing the practice will solidify your understanding.